Now, lots of functions come to us written out as a power series. So we can already think of a certain rational function as a power series. If I've got 1 divided by 1 minus x, as long as x is small enough, this is the very same thing as the power series summation of x to the power n. Again, as long as n starts at 0, goes to infinity, and my x here needs to be less than 1 in absolute value. That's a very important condition here. So some functions, right, like this rational function right here, in a certain region, as long as my x is small enough, this rational function can be represented by a power series. And depending on where you end up going, what your major is, you'll very likely encounter other functions that come to you written as a power series. So here is one example of such a function. The full name of this function it's a Bessel function. It's named after a person who worked with these things. The short name for function notation is just j sub 0 of x. There's a whole family of these things. Don't worry about them for right now. And the formula to calculate, if I have my input x, what is the value of this function at coordinate x? Well, we are instructed to compute the infinite series starting at n equals 0, going to infinity, where our individual summands look like negative 1 to the power n times x to the power 2n, all on 2 to the power 2n times n factorial squared. Now, that's very interesting looking formula. I find this to be fascinating where this came from. It's a little bit beyond where this course is going to be for the rest of this term. But just for if I was told to do anything with a formula like this, how would I do that? How would I do normal mathematics on a function whose formula is given to me as a power series? Well, to evaluate any series, any infinite sum, I'm going to look at the partial sums and try to determine if there is a limit to the partial sums as my n goes to infinity. Every single infinite sum is really just a limit, right? There is a limit built into here. If I can evaluate this limit and I get a finite number, then that's the output of my function. If I try to evaluate this limit and it diverges, then the function just isn't defined for that value of x. So I'm going to take a partial sum, start at I equals 0. I here is a placeholder variable, go up to n. So this would just be some funny looking polynomial. We can calculate polynomials. For whatever value of x we like, we can calculate a polynomial evaluated at x. Then we just have to take the limit as my nth polynomial, my nth partial sum, goes to infinity. So let's try to look at these things. Here are the first couple partial sums of this Bessel function. So S0 is just 1. S1 is 1 minus x squared on 4. S2 is 1 minus x squared on 4 plus x to the 4 on 64, and so on. And here are their graphs. So it looks like my constant S0 is in black, and then the later partial sums are graphed in different colors, blue, maroon, red, green, yellow, and so on. And notice that they all seem to agree the closer I am to 0, and then they disagree the farther away I get from 0. So depending on what number we choose for x, a shorter partial sum could be a better approximation. And then as we get farther away, we need to take larger partial sums to get good approximations.